Welcome to Jump into STEM student competition. My name is Dr. Mini Malhotra. I am a research staff member at the Oak Ridge National Laboratory. This pre-recorded presentation is meant to provide background and additional information for the challenge topic, keeping it cool or hot. This topic relates to utilizing thermal energy storage in buildings, which is one of the strategies to help fight climate change and adapt to its effects. The global economy has been heavily reliant on fossil fuels for centuries. In the US, about 80% of energy that we consume in buildings, industries, and transportation is derived from fossil fuels. Burning fossil fuels releases excessive amount of greenhouse gases into the atmosphere, which traps heat, much more than what is required to keep the planet warm enough to sustain life. This process is a major driver of global warming and climate change. To fight climate change, fossil fuel use must be curbed. The United States has set goals to gradually reduce greenhouse gas emissions and achieve net zero emissions by 2050. One of the key transformations needed to achieve these goals is economy-wide transition to renewable energy, which requires shifting from fossil fuel-based technologies in buildings, industries, and transportation sector to electric alternatives powered by renewable energy sources. Energy storage is crucial to enable transition to renewable energy. The renewable energy availability is intermittent and fluctuating based on the time of day, season, geographic location, and weather variations. This makes it difficult for the power grid to keep a steady balance between supply and demand. For example, as you can see on the left, solar energy supply is not aligned with the daily electricity demand profile. By utilizing energy storage, balance between supply and demand can be achieved, as shown on the right. With energy storage, surplus solar energy can be stored and used later when demand is higher than supply. Energy storage can be used for reducing peak demand by shifting loads to off-peak periods. Besides supply and demand balance, energy storage systems can also be used as an emergency backup during power outage. Energy storage is essentially the process of charging a storage medium with some form of energy, holding it for a duration, and discharging it when the energy is needed. Depending on the form of stored energy, energy storage systems are categorized. And when the stored energy is heat or cold, it is thermal energy storage or TESS. TESS technologies can be categorized based on how the thermal energy is stored, at what temperature, for how long, and the scale of application. Let's first review the scales of application of TESS. Grid scale technologies are integrated into the electrical grid infrastructure at the utility or regional level. District scale technologies use centralized infrastructure for the storage and distribution of thermal energy for heating and cooling across multiple buildings. Building scale technologies, which is the scope of this challenge, focus on providing energy management and load shifting capabilities for heating, cooling, and hot water systems within individual buildings. TESS technologies also have significant applications in industrial and transportation sector. In the next slides, I will focus only on building scale applications. High temperature storage and low temperature storage is sufficient to categorize building scale tests by storage temperature. Some technologies are suitable for both heat and cold storage. For power generation, district level applications and industrial applications, energy is stored at very high temperature, above 100 to several hundred degrees centigrade. For building applications, some technologies allow short-term storage for few hours to a day, whereas some technologies can store heat for several days, weeks, or even months. Short-term storage is suitable for demand-side management and load shifting, and also for renewable energy system when supplemented by grid electricity supply. Long-term storage is particularly suitable for applications when renewable energy system has to provide year-round energy supply to the building. Test technologies can store energy as sensible heat, as in water tanks or concrete in the building, where a solid or liquid storage medium undergoes temperature change. Energy can be stored as latent heat, as in phase change materials, where heat is absorbed or stored or released during a phase transition, such as solid to liquid or liquid to gas, without a significant change in temperature. Energy can be stored as thermochemical heat, where heat is absorbed and released during reversible chemical reactions. A number of parameters are used to characterize the performance of test system. For example, energy storage density, energy storage efficiency, charging temperature, and charging rate. For higher performance, high storage density, high efficiency, low charging temperature, fast charging rate are desired, and of course lower cost. Different test systems and materials have their advantages and limitations. In this figure, the performance of sensible and latent tests compared to thermochemical tests is shown. Sensible and latent tests have lower charging temperature and lower cost than thermochemical tests, but they do not perform well on other scales. Of course, when we review specific test materials of these types, we will find some variations. Advanced and hybrid test technologies are being researched and developed to overcome the disadvantages of basic tests. By combining different test technologies, we can leverage their strengths to achieve optimal performance. In buildings, tests can be utilized through passive applications where the charging and discharging process is natural. An example shown here is energy storage in the high thermal mass walls of the building. The walls would store heat from the incident solar and release during the night. With night ventilation in the summer, they would store cold at night and would make the indoors cooler during the day. In active applications, energy can be stored in the building materials, building systems, or standalone systems in the building, and the charging and discharging is managed actively. Active applications also include technologies where energy is stored in the vicinity of the building. Such system can serve one building or several buildings, as in a campus. Passive thermal energy storage typically provide short-term storage only. For seasonal or long-term storage, active solutions are considered. In this challenge, we ask students to develop innovative technical solutions for thermal energy storage for buildings to optimize energy use, enhance sustainability, and increase resilience. The solutions could involve but are not limited to the integration of materials, systems, and controls for the storage and release of energy. Also, the cost of implementing tests should be affordable or recoverable from the benefits provided by the tests. You may develop building type-specific solutions. For example, design strategies for integrating tests in a house, a multifamily building, a school, a hospital, or a supermarket, for new construction or in existing buildings. Here, you would assess the energy use and demand pattern for the selected building in a selected climate locations, assess the availability of on-site renewable energy if integrating those systems, and develop your solution around that. You may develop building system-specific test solutions, utilizing building structure, HVAC and water heating systems, or on-site renewable energy systems. You may consider recovering waste heat in the building, for example from ventilation system or heat rejecting systems and appliances. Here you may start by selecting the building system you want to focus on, investigate properties of storage materials, their storage performance, benefits, limitations, compatibility with the selected building system, and develop your solution around that. Or you may develop an adaptable technology solution and identify key applications where your solution would be most beneficial. You may develop controls-based solution for optimizing the charging and discharging cycle of tests, accounting for real-time energy demand, weather forecasts, and occupancy patterns. To make sure that these solutions are cost-effective for the customers, you may combine it with an innovative business model. For example, demand response programs or time of use pricing where customers can adjust or shift energy usage. The result is reduced electricity bills. A relatively new concept is tests as a service, where third-party providers install and maintain the system under flexible contracts and pricing models. Energy sharing networks is a collaborative approach among neighboring buildings to share and trade stored thermal energy based on their respective needs and surpluses. This slide contains links to additional sources. These are meant to provide you context and a starting point for your own investigation. You can also check the references cited in the challenge description. We hope this presentation has been helpful at introducing this challenge topic and has generated interest in potential innovative solutions. Please refer to the jumpintostem.org website for all challenge-related information. Thank you and good luck.